Hello everyone. Today we are going to solve questions from quantum chemistry which came in the December NET 2018. So the first question which we are going to deal is this one. Here the question is, one of the vehicle molecular orbital of 1,3-butadiene is this. The energy of this orbital in terms of Coulomb and resonance integral is, 4 options are given. So this is one of the wave functions of 1,3-butadiene. We know that there are 4 wave functions of 1,3-butadiene. So we have to identify which wave function is this, and corresponding energy is one of them. So we have to see which energy corresponds to this wave function. So first of all, let us see how to calculate the energy of 1,3-butadiene. So for 1,3-butadiene, the secular determinant in terms of alpha and beta is given as this. This is the secular determinant. This you have to memorize. Okay. And then for solving this, whole secular determinant is divided by beta. So we get this. Then we assumed alpha minus beta equal to E. This is the assumption made. Okay, this assumption we will again use we will use later. So after making this assumption, we will put alpha x in place of alpha minus E divided by beta. This is the determinant which we got. Afterwards, we will solve this determinant by using the basics of matrix. So it splits up into 4 determinants. Out of them, the 2 terms are 0. Then we will solve these 2 terms d1 and d2. You can pause the video and see the calculation. So d1 and d2. The calculations are simple. Class 12th matrix basics are used here. So d1 and d2, after solving this, we get this one and this one. Okay, then we put this value in here, then this value here. We get this expression. After solving the expression, here we have assumed I have written x to the power 4 as x square to the power 2. Then I have made another assumption, x square equal to y. Then it takes form of the quadratic equation, then used simple quadratic formula to solve y. After solving y, I got these 2 values. I have solved x because y equal to x square, then x equal to plus minus y. So 4 values of x came. Again, the earlier I have made assumption, so this assumption is alpha minus E divided by beta equal to x, then E equal to alpha minus beta x. This is the just I have rearranged. Then in place of x, since I have 4 values of x, one by one I put the values of x, then I get 4 energy expression, E1, E2, E3, E4. Then this we should know that alpha value is around 0 kilojoule per mole and beta is minus 75 kilojoule per mole. So after substituting beta and alpha value, this E1 value is the most negative. The most negative means least energy, and least energy corresponds to the lowest wave function. So I have arranged this is the least energy, then this, then this, then this. So E1, E2, E3, E4. E1 corresponds to wave function psi1, E2 psi2, E3 psi3, and E4. So these are the 4 wave functions I have written. So you can memorize these wave functions using this simple technique by seeing the signs of the wave lobes. Positive, all positive, so all positive sign. The here lobes positive, positive, negative, negative. So positive, positive, negative, and negative. So here is one node, so the value the signs are different, plus and minus. Here there are 2 nodes, so plus minus and minus plus. Here there are 3 nodes, plus minus, then again sign change, minus plus, plus minus. So here you can see plus minus plus minus. In this way you can remember the signs. In the question, the sign is positive, positive, then negative, negative. In the question you can see the sign is positive, then positive, positive, then negative and negative. So therefore the wave function is, from here you can see it is psi2. So the corresponding energy is this, alpha plus 0.618. you can also write alpha plus 0.62 beta. So therefore the answer is second, alpha plus 0.62 beta. Okay. Now let's move to second question. So for a one-dimensional harmonic oscillator perturbed by an x cube potential, the sum of first order and second order correction to the ground state energy. So you have to calculate the first order and second order correction. Perturbation is also given, x cube is the perturbation given. So the first order correction is given by, this is the formula of first order correction. Delta E, it is first order correction, is given by, this is the expression. Here in the expression, this is the wave function of unperturbed system. Okay, and this is also the wave function of unperturbed system. This delta H is perturbation. So here we have given perturbation x cube. So I have solved. Here I have kept the value x cube, and here in place of wave function I have used the wave function of simple harmonic oscillator. These are the values. Here the constant values beta by pi and beta by pi I have solved, and they came outside the integration. Beta by pi half, and this x cube, and this solved the exponential part. So here is beta x square by 2, here also beta x square by 2, both in negative, and minus minus is plus, so I have added, so I have got minus beta x square. Now for solving this integration, you can remember this formula. This is the simple formula. Here is x to the power n e to the power minus ax squared dx. Okay, if the n value is odd, then the whole value of integration is 0. You can remember like this. This simple formula integration you need to memorize. And if n is even, so you can get gamma n plus 1 by 2 a to the power n plus 1 by 2. Since in our case the n value is negative, n value is 3, which is odd, so therefore this value is 0. Therefore first order correction delta E is also 0. Okay, so you can simply remember one trick. If there is odd power of x in the perturbation, in case of ground state, you must remember this. In case of ground state of SHO, then first order correction will always be 0. So here is x cube, so first order correction for the ground state is 0. If there is x, then also first order correction for the ground state will be 0. If there is x to the power 5, then also it is 0. Okay, so therefore first order correction is 0. Then let's see second order correction. This is the formula of the second order correction. This formula is for second order correction, and for second order correction also you should know this trick, that second order correction to the ground state is always negative. So therefore first order correction is 0 and second order is negative, so therefore the value is either 0 or less than 0. So therefore sum of first order and second order correction to ground state is always less than 0. So therefore the option which is correct is fourth option, less than or equal to 0, the sum of first order and second order correction to the ground state. Now let's move to next question. Difference in the average values of the position for state n equal to 1 and n equal to 2 of a particle confined in one-dimensional box of length L. So first of all I have to calculate the average value of the position x. Average value of any observable is given by this formula. Chi star, then A, then chi, then d tau. Average value of position operator is given by x. Then since in the question it is given one-dimensional box, so I have used wave function of one-dimensional box, then x, then again wave function of one-dimensional box. Both are same, chi star and chi are same because no iota terms are there. So I have solved this root 2 by L and this root 2 by L, since they are constant, so they came out of the integration, and x is there, and sine square and pi x dx by L. Then I have this I have applied the formula. Sine square theta is given by 1 minus cos 2 theta by 2. So 1 minus cos 2, then theta value, then divided by 2. So this 2 will come outside. Then I have applied integration formula. So basic integration is used. Then here integration of x is x square by 2. Then these are the limits. Then cos, integration of cos is sin x. So sin x by this value. So ultimately the average value come out to be L by 2. So therefore, since the average value of x does not contain any n value, so therefore for n equal to 1 it is L by 2, and for n equal to 2 also it is L by 2. So therefore difference between both is obviously 0. So the correct option is option 4. The difference is 0. Let's move to next question. The question is, the Hermitian operator among the following is. 4 options are given. Out of these 4 options, which one is Hermitian operator? So we must know all the operators given in the postulates of quantum mechanics are Hermitian. And if we see this one, this is the operator of momentum, minus iota h cut ddx. So therefore momentum is a Hermitian operator. Therefore correct answer is 2. You must memorize this Hermitian operator. This is the Hermitian operator for momentum, minus iota h cut ddx. Then px square minus h cut square ddx square. Then kinetic energy Hermitian operator. This is the angular momentum Hermitian operator. So you must memorize all these Hermitian operators. So out of this, the second option is the momentum operator, and therefore momentum operator is Hermitian. Therefore the correct answer is 2. Thank you everyone for watching the video. If you like the video, please subscribe to my channel and hit the bell icon. If you have any queries, please do comment in the comment box. Thank you everyone.